So, we will continue our discussion on the indicator diagram of a reciprocating pump, rather a positive displacement pump. So, we have discussed yesterday the the ABCD is the most simple one, that is the indicator diagram, pressures versus volume. But while we have described the ABCD, that is suction and delivery stroke, and while we are discussing, that time we did not consider the effect of inertia, that is because of the liquid volume in the pipelines, and also the frictional effects in because of the fluid flow through the pipes. And also we have discussed that if we take into account the inertial effects, I mean then we have modified indicator diagram, that is EMF. So, modified indicator diagram concerning inertial pressure will be EMF GNH, that is the modified indicator diagram. Now, if we again consider the frictional effect, that is always there, I mean we cannot ignore. So, what will be the how the frictional effect will modify the indicator diagram, and that we need to look into, I mean that we should now discuss. So, you know that what we know, I mean how we can calculate frictional losses in the pipeline, whether it is suction pipe or delivery pipe. So, if we go back to my previous slide where we have plotted, where we have described about suction pipe and delivery pipes through which fluid is flowing during suction and delivery stroke. Okay. Now, while fluid is flowing through suction pipe and delivery pipe, we cannot ignore the frictional effect. So, even if we draw the indicator diagram modified with the inertial effect due to the presence of liquid volume in the pipelines or the suction pipe and delivery pipe. So, the modified indicator diagram will be like this. So, this is volume and this is absolute pressure, right. So, this is volume, this is absolute pressure, and if this is the atmospheric pressure, so this is atmospheric pressure, then this one was the suction stroke. So, then there will be a rise in pressure for constant volume, this is delivery stroke, and this one is sudden fall in pressure. So, we have given name A, B, C, D, and then this is a simple indicator diagram where we did not take into we did not take the effect of effects of inertia and frictional into account. Now, considering the effect of inertia, the modified indicator diagram, that is what we have discussed in my last lectures, that will be like this. So, it will be like this, and EMF, similarly there will be rise in pressure, and the modified indicator diagram will be like this, EMF GNH. So, the modified indicator diagram concerning the effect of inertia will be EMF GNH, that is what we have discussed last day. So, now we need to take the effect of frictional effect into account. So, whenever fluid is flowing through suction pipe or delivery pipe, normally we do calculate frictional losses following Darcy-Weisbach equation. So, if we write down the Darcy-Weisbach equation, that is basically frictional head loss HF is equal to FL by D V square by 2G, where V is the fluid velocity, L is the length of the pipe, F is the friction factor, and D is the diameter of the pipe. Sometimes F is replaced by 4F because that depends upon whether fanning friction coefficient or the whether it is F is equal to 64 by RE or 16 by RE, that depends upon. Now, that is not an important issue. So, there is FL by D V square by 2G is the frictional loss. So, from this expression it is quite clear that the frictional head loss HF will vary or will be proportional to V square, that is the velocity square. So, now if we try to modify, this V square is the basically fluid velocity. Now, I can replace the fluid velocity in terms of the piston velocity. So, V is the velocity of the fluid. So, it is fluid velocity. This fluid velocity can be replaced or can be written in terms of the velocity of the piston, that is U, that will be that is what we know how V is equal to A by small a into u, where A is the cross section area of the cylinder, small a is the cross section area of the pipeline, whether it is suction pipe or delivery pipe, and this u. So, if I now write this equation in a, if I write this, so then frictional head loss will be HF FL by D, it depends upon then A suction or delivery whatever it is. So, I am not writing, so A by A square into u square by 2g. So, this will be the total frictional losses. So, the indicator diagram whatever we are plotting, that is essentially in the cylinder, I mean how the cylinder pressure and volume is changing. So, we have now replaced velocity of the fluid in the pipe in terms of the piston velocity, where piston velocity is u. Now, L and A by A, these are variable, because L may be LS or LD and A may be AS AD, depending upon the suction pipe and delivery pipe, whatever it is, but we can replace it, we can write in terms of the piston velocity. So, what it is clear, in fact what it is seen that Darcy equation, whatever it is, but Darcy equation varies HA versus V square. So, if we now try to superimpose that effect on the modified indicator diagram, that is what we have drawn, that EMF GNH, then of course now I can write something that how we can this piston velocity may be, this is very important. So, the frictional effect will be parabolic in nature, that is quite obvious from the equation HF versus V square. So, the HF proportional to V square, from where it is quite clear that the variation will be parabolic in nature, but somehow we need to calculate the piston velocity. So, how do we calculate piston velocity? So, if we go back to my previous slide, where we have written that sorry, this will be theta, this angle will be theta, instead of this angle will be theta, and this will be 180 minus theta. So, if piston, let us say, is moving a distance x from its initial position. So, if piston moves a distance x from its initial position, maybe piston was, piston is moving, let us say, x distance in this direction, let us say x distance is moving, and because of what, crank has connected, let us say, angle theta, and so I can now calculate this, maybe this distance is x. So, I can calculate what is this distance x, linear distance. So, because of the crank revolution by an angle theta, if there is a linear displacement of the piston is x, then I can calculate x in terms of the frequency omega, crank radius r. If the crank radius is, let us say, r, crank radius is r, then I can replace the linear displacement x of the piston for a angular displacement by an amount theta in terms of crank radius r and frequency omega. Now, if I try to express the, that is very important, that is piston velocity. So, how I can calculate piston velocity is very important, because that is important to obtain. Maybe grossly the effect of friction will be parabolic in nature. I mean, if you would like to modify the indicator diagram, then of course we will be parabolic in nature frictional effect. But how we will calculate where the velocity will be 0, where acceleration will be maximum, to know that we need to calculate the piston velocity. How we can calculate piston velocity is very important. So, piston velocity, this is very obtained. How we can calculate piston velocity? This piston velocity may be obtained from the displacement equation. So, if I recall that if this is my piston and piston is moving like this, so this angle is theta. So, this is 180 minus theta. So, let us say this is the axial displacement x. So, I can calculate, and radius is r. So, r is the crank radius, omega is the frequency of the rotation of the crank, and then piston velocity can be obtained from the displacement equation assuming simple harmonic motion, and it can be written in terms of, so we are assuming that the displacement equation following the simple harmonic motion, and we can calculate piston velocity in terms of the crank radius r, and also the omega, that is the frequency of the crank, rotational speed of the crank, rather we can write that is rotational speed of the crank. rotational speed of crank, and theta is what? Crank radius. This is theta is what? Theta is the crank angle. So, this is crank angle. So, assuming the simple harmonic motion, that the displacement equation follows the simple harmonic motion, and we can calculate piston velocity in terms of crank radius, rotational speed of the crank, and crank angle theta. By how? So, then how we can calculate this is very important. So, you know that as I said you, from this figure I can write that the linear displacement x for an, suppose initially when piston was at the cylinder end, then initially this point, let us say this is P, this point P was here. So, now P has moved a distance by an amount theta, by an angle theta, and for that we have a linear displacement x. So, this linear displacement x can be calculated from this triangle. So, this x will be how much? R minus R cos 180 minus theta is cos theta. So, now this theta is equal to R minus R cos omega t. So, I can obtain dx dt, that is velocity of the piston, is equal to R omega sin omega t. So, how we can calculate? So, if I know the linear angular displacement, suppose piston has a linear displacement x, and for that crank has rotated by an angle theta. From there we can calculate linear displacement x in terms of crank radius and crank angle, while omega is the rotational speed of the crank. From there we can calculate what is the piston velocity dx dt, that is R omega sin omega t. This is very good. Now, so u will be omega into R into sin theta. So, this will be R omega and sin theta. So, piston velocity, that is piston velocity will be u is equal to R omega sin theta. So, it is quite clear from this equation is that when theta is equal to 0 or theta is equal to, I mean that is at the beginning. So, for theta is equal to 0, that is at the beginning of and rather at the beginning of and at the end of each stroke theta is equal to 0. If theta is equal to 0, that means u will be equal to 0. So, at the beginning as well as at the end of at the beginning and end of each stroke theta is equal to 0. So, velocity will be 0. If velocity is 0, right, then fluid frictional effect will be 0 following this Darcy equation. So, fluid frictional effect will be equal to 0 from the Darcy equation. This is very important. So, what we obtain, that at the beginning and at the end of each stroke theta is equal to 0. So, velocity will be 0. So, fluid frictional effect will be 0, but the acceleration or deceleration whatever it is, it will be maximum, right. So, but the acceleration deceleration du dt, but the acceleration or deceleration, that is du dt, will be maximum. So, this is very important, that at the end and beginning of each stroke fluid frictional effect is 0, but the acceleration and deceleration is maximum. Similarly, at the middle, I mean at the middle of the when the velocity is maximum, that is at the middle of the stroke. Similarly, at the middle of each stroke, that is at theta is equal to either 90 degree or 270 degree, right. So, theta is equal to 90 degree or 270 degree, fluid frictional effect will be maximum because velocity will be maximum, but the acceleration and deceleration will be 0. So, u is equal to u max. So, fluid friction will be maximum, fluid friction will be maximum, but the acceleration deceleration will be 0. So, now if I try to superimpose the effect of friction on the modified indicated diagram, then how it will look like. So, what you obtain that at the end and beginning of each stroke, so theta is equal to 0 and fluid friction effect will be no fluid friction effect, rather acceleration deceleration will be maximum. So, and at the middle velocity will be maximum, while the acceleration and deceleration will be 0, no acceleration deceleration. So, and we need to keep in mind that frictional head loss varies, it is parabolic in nature. So, if I try to superimpose that effect, so here it will be like this and this will be like this, right. So, this will be the actual modified diagram. So, this is the suction stroke, this is suction stroke and this is the delivery stroke. So, the actual indicated diagram modified with the effect of inertia as well as effect of fluid friction, it will be, let us say it will be E cube F G S H. So, I am writing that the actual indicator diagram considering fluid friction as well as inertia will be E cube F G S H. So, this is very important. The actual indicated diagram considering the effect of fluid friction as well as inertia will be E cube F G S H. This is very important. Okay, fine. So, this is what is very important that we have calculated. Now, we need to know a few important aspect to solve a few problems. I mean, when you are going to solve numerical problem, that means what will be the flow rate from the positive displacement pump, and for that we have to work out a few exercise. I mean, we need to do some exercise to calculate that what would be the volume flow rate and then what will be the efficiency like this. Okay. So, if we go to the next slide, then we can write that whenever piston is moving, then the instantaneous pressure in the cylinder P is P. Suppose how we can calculate work done. So, this is important. So, work done. So, if we assume P is the instantaneous pressure, so P is the instantaneous pressure in the cylinder, of course in the cylinder. If P is the instantaneous pressure in the cylinder, then the force exerted by the fluid on the piston, of course, then how we can calculate? Then force exerted by the fluid on the piston will be how much? That will be how much? A into P, where A is the area of the piston face, area of piston face. So, this is the work done. So, force exerted by the fluid on the piston will be AP, then, and for that if piston has a displacement dx, then work done will be, right. And if piston moves dx distance, and then instantaneous work done will be how much? AP into dx. Then instantaneous work done, then instantaneous work done AP into dx, AP into dx. So, the total work done total work output or total work done during cycle will be W will be equal to AP dx, that is P into dx, area is constant. So, this is the total work done, AP into dx. So, how we can calculate? That is the area under the indicated diagram. So, this is the total work done. Now, question is how much volume of water is displaced, I mean delivered by the pump, and how we can calculate. So, this is very important. So, volume of water or volume of liquid displaced will depend upon the speed of the pump, and that will be V is equal to A into S, where S is equal to piston stroke and V is equal to swept volume. So, this is the swept volume and S is equal to stroke length or piston stroke, rather piston stroke, and A is the, that is what I have told, area. Now, the volume of the liquid displaced will depends, this will depends upon the pump speed, right. So, volume of liquid displaced will depend upon the pump speed, and that will be A into S, where S is the piston stroke and A is the area and V is the swept volume. Then Q, that is the discharge. I do not know whether it is theoretical or ideal or theoretical or actual. So, discharge will be how much? AS into, rather V into omega, rather AS into N, where N is equal to omega by twice pi. So, that will be equal to how much? So, Q will be equal to V into omega by twice pi, where AS is equal to V. So, now this is the theoretical one. So, this is the theoretical discharge. This is theoretical discharge. Why it is theoretical discharge? Because there will be certain amount of, as I said you, that positive displacement pump, rather reciprocating pump is a kind of PD pump, which is normally used to have to deliver high pressure while flow rate will remain constant. So, we have calculated that volume of liquid displaced. That is very important quantity that we need to know, because essentially we are installing one pump only to obtain high flow rate. Of course, discharge head will be important. So, we will work out again how do we calculate total head, that is another issue, but the volume. So, in one stroke length, I mean one stroke, how much volume? That is a swept volume, that is area into S. A is the piston area. So, now S is equal to piston stroke. So, A into S, that is V is the swept volume, and if the speed is N, then of course V into N will be the total theoretical discharge, where N is equal to omega by 2 pi. So, if this is the case, then I have calculated this theoretical discharge, but this theoretical discharge, this discharge is theoretical one, because we won't get this amount of discharge whenever piston is moving towards the end of the cylinder, and it will try to develop high pressure. There will be certain amount of leakage through glands, through valves, and so we should not get this amount of discharge, rather actual discharge should be always less than that. So, that is why, if I go to next slide, so what is important? So, this Q, that is equal to V, that is equal to V into omega by 2 pi, this is theoretical discharge. This is theoretical discharge. So, I am writing Q theoretical. So, Q actual will be Q theoretical minus, there will be loss, small q amount, this will be loss, leakage loss through glands, etc. So, there will be certain some amount of loss, rather that through the gland, etc., because whenever cylinder is put moving towards the end, there will be high pressure. Because of that high pressure, there will be certain amount of leakage loss through the glands, etc. So, Q actual will be always less than the theoretical one, and that is why one efficiency is defined, that is known as pump efficiency, and that rather volumetric efficiency, that is known as volumetric efficiency of the pump, eta V, that is equal to Q actual by Q theoretical, right. And since there will be certain amount of loss, so we are considering, and that is known as slip. Sometimes liquid slips, it it won't go to the delivery sum. So, that slip factor, slip is defined Q theoretical minus Q actual divided by Q theoretical by Q theoretical. So, that will be 1 minus eta V. So, this is known as slip of a PD pump. Actually, if I now try to draw the H cube curve of the positive displacement pump. So, if I try to draw that, if this is head developed by the pump and this is the discharge by the pump, ideally we will have higher discharge, the flow rate will remain constant. So, ideally the curve like with this. So, this is the ideal one, but to take into to take the effect of slippage into account, rather considering the effect of slippage, slip will be there, because whenever fluid piston is pushing, that the piston is moving towards the end, it is always trying to pushing the liquid, as a result of which of course we will have a high pressure, and because of that high pressure some amount of liquid will leak through the glands and also the valves, as a result of which we may not get this amount of discharge, rather actual discharge will be always less than the theoretical whatever we have predicted. So, the actual curve will be like this. So, this is the actual curve. So, actual discharge from a PD pump will be always less than the theoretical discharge predicted by that quantity swept volume into omega by twice pi. Omega is the rotational speed of the crank, and it is because of the slip. So, the existence of slip, that is the leakage of fluid through the glands. Okay. So, till now we have calculated the volumetric efficiency and we have an idea about the discharge through a PD pump. So, that is one aspect, and now how do we calculate the head developed by the pump? That is another important point we need to take into account. So, how do we calculate head developed by the pump? This is very important again. So, and for that what we have to do, we have to calculate, we have to go back to our slide where we have drawn the schematic. So, if we go back to my previous slide where we have drawn the schematic, and from here we can tell that what will be the total H. So, this is very important, and total head developed by the pump will be how much, and I am telling now. So, here if I now try to energy balance, right. So, the pump pressure will depends upon the system, it is very important. The pump pressure, the pressure that will be developed by the pump, that or the head developed by the pump will depend upon the system in which it is acting. So, if I apply energy equation between that is why I am trying to go back to my previous slide. If I apply energy equation between point, let us say 1 and 4, that is if I go back to my previous slide, and if I let us say this is my point, this is point 1 and this is point 4. So, if I now try to write energy equation between the point 1 and 4, what I get, and that is what I will try to write over here, that if I, as I said you, the pump pressure that will depend upon this system in which it is working, and if I try to write energy equation between point 1 and 4, then what can I obtain? So, now we will discuss about the head developed by the pump. So, head developed by the pump. Last slide we have discussed about the discharge, and there will be a theoretical discharge and actual discharge. Theoretical discharge is predicted by that quantity, that is swept volume into omega by twice pi, while the actual discharge will be less than that. But what will be the head developed by the pump? Right, what will be the head developed by the pump? This is very important. So, if I apply energy equation, between points 1 and 4 in the schematic, points 1 and 4 are depicted in schematic, right. So, points 1 and 4 are depicted in the schematic. If I try to write energy equation between these 2 points, what I can write? Very important. So, it is very simple, that total energy at 1 plus work done by the pump, of course that is work done by the pump will be equal to how much? Total energy at 4 plus frictional losses. This is quite simple, because energy at 1 is the atmospheric pressure, that we know, and we are taking water in the pump, rather we are sucking water in the pump, and then we are working on that fluid, that is work done by the pump, and whatever energy you are getting at the point 4, that will be equal to the energy at point 12 plus energy plus work done by the pump. And of course, while we are lifting water, let us say from point 1 to point 4, we cannot ignore the frictional losses. So, that amount of energy that we need to overcome using energy at 1 plus pump work. So, that is the total equation. So, what is the total energy at 1? So, if I write, let us say this is quantity A, this is quantity B, this is a quantity C, and this is the quantity D. So, A is how much? That is total energy at point 1 per unit mass of fluid flowing. So, total energy at 1 per unit mass of fluid flowing will be how much? P A by rho, this is P A by rho, very important. Work done by the pump is how much? This is very important, B. Work done by the pump is simply G into H, where H is the head that will be developed by the pump. So, H is the head that will be developed by the pump. So, that work done by the pump is GH. Similarly, C, that is total energy at point 4, of course per unit mass of the flowing, per unit mass of fluid flowing is equal to again P A by rho plus something. What is that? Because that is not the atmospheric pressure, plus if the total height Z, then G into Z, right. Z is the distance between points 1 and 4. So, if the height difference between points 1 and 4 is the Z, then Gz is the energy, the total energy that will be at point 4, and finally D is the frictional losses. We will have two component, frictional losses in the system, rather pipelines will be how much? Will be G into summation of H1s plus G into summation of H1D. So, this is the losses in the pipeline suction, this is the suction side, suction pipe, and this is the delivery pipe. So, we have obtained. So, frictional losses in the system. So, we have obtained this 4 quantity, and if I rewrite this equation, what I will get? So, if I go to the next slide, then I will get P A by rho plus work done by the pump is G into H, that is equal to energy at point 4 Gz plus P A by rho plus G into summation of H1s plus G into summation of H1d. This is the equation whatever we are getting. So, what we obtain, that is, so if I rearrange this equation, I obtain that head developed by the pump will be simply equal to G plus summation of H1s plus summation of H1d. So, this is the head developed by the pump. So, this is the pump head. Now, this is very important that capital Z is the height between the rather distance between points 1 and 2, this is very important. So, while we are calculating total pump head, then I can split this equation into different parts. I can obtain that what would be Z, Z will be equal to the suction lift and plus delivery height. I mean, we are sucking water from the reservoir, suction sum, and then we are discharging to the delivery sum. So, there will be a height difference between suction sum to the pump axis, that is ZS, suction lift as well as there will be delivery lift. So, suction lift as well as delivery lift, these two will be the total height, that is Z. So, now how we can calculate the suction lift and the delivery lift in terms of other quantities like pressure and frictional losses, and for that we need to apply again steady flow energy equation between a few points. So, if we do that exercise, then I may obtain that what will be the actual head developed by the pump, and then what will be the overall efficiency. This is very important. You know that if I go back to my previous slide, schematic rather, this is very important. So, what I am trying to write, see, suppose the suction side, say this is point 1 and this is point, and from this I am telling that this is the suction height. So, ZS. So, this is whatever I told that is ZS, and similarly this point will be ZD, that is delivery lift, suction lift plus delivery lift, and this is the amount which is very important, that is below atmospheric pressure. I mean, if I now try to write the, suppose I try to write steady flow energy equation between lower reservoir and the pipe at the pump inlet. So, suppose I am writing Bernoulli equation between this point 1 and this is 1 prime and this is 2 prime. So, I am now writing that steady flow energy equation between point 1 and 1 prime, then what I will get, that is the lower reservoir as well as the pipe at the pump inlet, then what I can obtain. So, I can obtain, again I have to go to the next slide. So, if I write steady flow energy equation between lower reservoir and pipe at the pump inlet and pipe at pump inlet, that is between points 1 and 1 prime, then how can I write? PA by rho g will be equal to, let us say, pressure at the pipe at pressure at point 1 prime is PS rho g plus VSS square by 2g plus ZS plus summation of H1s. So, I can obtain that static pressure PS by rho g will be equal to PA by rho g minus this quantity VSS square by 2g plus ZS plus summation of H1s. So, this expression in the bracket which is known as manometric suction head. So, this is manometric suction head and we write it HM. Now, note that if I now go back to my previous slide where we have drawn the schematic. So, this is the quantity, I mean will be equal to summation of H1s plus Vs square by 2g, that is less than the atmospheric pressure. Of course, Zs should not be there. So, this is the quantity that will be H1s plus Vs square by 2g, that is which is less than the atmospheric pressure that we obtained using the U-tube manometer connected at the pipe which is at the pump inlet. Fine. So, now again if I try to write Bernoulli or rather steady flow energy equation between delivery pipe, and now I will try to write I will try to write steady flow energy equation between point 2 and rather between point 2 prime and 4. So, what I will get? So, now I am trying to write steady flow energy equation between points 2 prime and 4. What I will get? this is very important. What I will get? PD by rho g, that will be equal to PD by rho g plus Vd square by 2g will be equal to Pa by rho g at 0.4 plus Zd plus summation of H1d. So, the static pressure at the pump outlet PD by rho g, the static pressure at the pump outlet, static pressure at pump outlet will be equal to Pa by rho g plus Zd plus summation of H1d minus Vd square by twice g, Vd square by twice g. So, again the quantity within this bracket which is known as the manometric delivery head. So, this is known as HMD, this is HMS. So, this is manometric delivery head, and if I connect and again YouTube manometer between these 2 points. So, this quantity will be equal to, this is very important, this quantity will be equal to H1d summation of minus Vd square by twice g. So, this is the quantity. So, the pressure at that point should be and this is known as the manometric, this quantity will be obtained by connecting a U-tube manometer at the pump delivery point, at the outlet of the pipe at the pump delivery point, and another end will be the open to ambience, the atmospheric pressure. From these two expression, what can I write? That we have obtained the manometric delivery head, manometric static head, and then from there the pump manometric head is defined. So, this is the, so what is the pump manometric head? So, pump manometric head HM will be HMD plus HMS. So, this will be the pump manometric head. Now, if I try to I obtain the expression of H, Z plus H1S plus H1D, right, and if I try to write the HMD and HMS. So, what is the expression of HMD and HMS? And if I write the expression of HMD and HMS, what I will get? I will get Z plus H1S plus H1D minus Vd square minus Vss square by twice g. So, this is I will get. So, after putting the expression of HMD and HMS from the previous slide, I will get this is the manometric head. Now, this is the manometric head, and we have derived the head that will be developed by the pump using total energy balance, energy balance equation. If we compare these two equations, so I have obtained H from energy equation, that H will be equal to how much? Z plus summation of H1S plus summation of H1D. So, that is what we have obtained, Z plus summation of H1S plus H1D. So, if I compare these two, and I can write H minus HM, H minus HM will be equal to Vd square minus Vss square by twice g. So, this is very important, Vd square minus V square by twice g. So, this is let us say equation 1, this is equation 2. So, comparing equation 1 and 2, comparing equation 1 and 2, I obtain H minus Hm is equal to Vd square minus Vs square by twice g. Mind it. So, if delivery pipe and suction pipe are of same diameter, then H will be Hm. So, if Vd is equal to Vs, that is delivery and suction pipe are of same diameter, in that case H will be Hm. So, manometric head will be equal to the head developed by the pump. So, you have to note it, right. So, H is equal to Hm. Now, what is the question is, the head developed by the pump H, the head developed by the pump H should be always less than, rather H plus some quantity is let us say frictional losses, H frictional losses Hp will be equal to the Hi, that is the internal head generation. Internal head generated by the pump, where HP is the friction inside the piston cylinder, right, but the pump is greater than pump head H, difference according to internal loss in the pump. So, this is the frictional losses in the pump. So, the internal head generated by the pump will be always higher than the head developed by the pump H, rather the pump head. So, this is the pump head. We cannot ignore, because fluid, we are putting pressure by piston, so there will be a fluid friction. So, if we take that effect into account, then the head, internal head developed by the pump will be always higher than the pump head by an amount HP, which is HP is the frictional losses. So, what will be the internal? So, what will be internal, fluid power generated by the pump will be equal to rho g cube, q theoretical or q, of course q theoretical you have to consider, into Hi, right, and actual pump, this is in actual fluid power generated by the pump will be equal to rho g cube theoretical into H. So, this is the internal fluid power generated by the pump, and this is the actual fluid power generated by the pump. So, now we are taking pump from the prime mover, the electrical motor. So, the overall efficiency of this is the internal fluid power. So, internal fluid power will be always higher than the actual fluid power generated by the pump, fine. So, to run the pump, normally what do? We take power from electrical motor. So, overall efficiency, we have defined volumetric efficiency. Overall efficiency of the pump will be defined as eta overall is equal to P by P naught, where P is equal to rho g q theoretical H divided by P naught. So, this is the actual, this is the overall efficiency. Now, I can write that overall efficiency P by P naught. So, I can write this P by P naught is equal to P by P1 by P naught into P by P1, rather, or Pi by P naught into P by Pi, where Pi by P naught I can that equal to Pi by P naught into what is P, rho g q theoretical into H divided by and sorry, this is P, I can write Pi is equal to, let us say internal, this is Pi. So, this Pi is equal to rho q theoretical into Hi, right, I am writing, sorry, this P is equal to H, this is equal to P H by rho g q theoretical into Hi, that is the internal fluid power. So, I can write Pi by P naught into H by Hi into this should not be Q, this should be cube, not Q theoretical. So, this will be cube. So, this is cube. So, that is equal to Q by Q theoretical. So, actual fluid power generated will be, of course, Q, because it is not ideal. So, actual fluid power generated will be rho g Q into H. So, not Q theoretical. So, what I obtained, Pi by P naught into H by H naught into Q by Q theoretical. So, that what I can write, that eta overall, this is what Pi by P naught is known as mechanical efficiency. So, this is known as mechanical efficiency eta m. H by H naught is equal to how much? This is the internal fluid power generation and this is the actual fluid power generation. So, H by H naught is known as the hydraulic efficiency. So, this is eta hydraulic and this is Q by Q theoretical is equal to eta overall volumetric efficiency. So, eta volumetric. So, I can write that eta overall is equal to eta mechanical into eta hydraulic into eta volumetric. So, this is very important, and we have been able to prove that the overall efficiency can be written in terms of three other efficiencies, that is mechanical efficiency, that is Pi by P naught, where Pi is equal to internal fluid power generation, because the internal power generation will be always higher than the actual power, because internal head developed should be higher than the actual head, because there will be some losses in the pump itself. So H by Hi known as the hydraulic efficiency, and eta V is the theoretical, Q by Q theoretical known as the volumetric efficiency. So rearranging these three terms, I mean I can write eta overall efficiency, eta O, that is overall efficiency in terms of hydraulic efficiency, mechanical efficiency and the volumetric efficiency. So this exercise will help us to solve the numerical problem, and so far whatever I have discussed, I think it will help us to solve numerical problem, as well as it will help to have a fair idea about how the reciprocating pump is working and how the head is being developed and what should be the volume flow rate. Also we have discussed that the H cube curve, why the actual cube flow rate is deviating from the ideal one. So with this I stop here today, and we will continue the next topic in the next lecture. Thank you.